In Chapter 3, we're going to spend essentially the whole chapter looking at this simple system of two equations. It's linear, homogeneous, constant coefficient, just exactly of this form, where a, b, c, and d are constant. Notice there's no t on the right-hand side, so this is autonomous. There's no f of t here, or g of t, and a, b, c, and d are constant. So this is a pretty simple system, but we're going to spend the whole chapter looking at it. And we'll often write it in matrix form. If A is the matrix A, B, C, D, then you can write your system as dy dt equals ay, where A is this matrix and y is the vector of two unknown functions, and dy dt is the derivative of vector xy. Most of what we'll do will apply to systems, larger systems like three equations and three unknowns. In that case, maybe x, y, z are your three unknown functions of t. You have a 3 by 3 matrix. This would be dx dt, dy dt, dz dt. And so generalizing to a system of n equations is fairly straightforward, but we can't generalize to nonlinear or even non-homogeneous problems. It has to be exactly this form if it's 2 by 2. Here's the more general system of n equations and n unknowns. We'll normally just talk about the 2 by 2 because it's obvious how to generalize to n by n. But this is the more general form. A would be an n by n matrix of constants. Y is a vector of the n unknown functions you're looking for. T is the scalar time. Now, why do we spend so much time on such a simple system? Well, there are important applications that are in that form or can be put in that form. For example, here's our damped harmonic spring oscillator. It can be put into the form of, it's a second order equation, but it can be written as a system of two first order equations by just defining v, the velocity, to be dy dt. Then dv dt will be the second derivative of y, and that's equal to, constant times y plus constant times v. So this is exactly the form that we'll learn how to solve. So there are some important applications that have this simple form, but not so many. The main reason why we spend so much time solving and studying this qualitatively in this chapter is we'll find out in Chapter 5 that more general problems, nonlinear autonomous problems like the predator-prey problems, they're what we learn about the equilibrium points and behavior around the equilibrium point of this system. We can apply it to what happens to the more general problems around their equilibrium points. Now, so notice that this system of two equations here always has an equilibrium point at x equals 0, y equals 0. So the origin, it's autonomous because there's no t on the right-hand side. The origin, x equals 0, y equals 0, is always an equilibrium point because if x and y are 0, then dx dt and dy dt are 0, so you stay there. More general systems like the predator-prey problems at Chapter 2, the equilibrium points are not necessarily at the origin, and they're not linear and homogeneous, but we'll find out in Chapter 5 that near their equilibrium points, the more general autonomous systems behave like these systems do around its equilibrium point 0, 0. So basically, if you look at the equilibrium point of the more general systems like the prey-predator problems, through a microscope, they behave just like this for some constants a, b, c, and d. They're very much like it. Remember, equilibrium points for a single equation are pretty simple because there's only two sides of an equilibrium point, above and below. And if an equilibrium point, if you start there, you stay there. If you start just above it and you get sucked into it, and just below you get sucked into it, it's called a sink. If you get blown away on either side, it's a source. If on one side you get sucked in, the other side gets blown away. So in a single equation, autonomous equation, and one unknown. Equilibrium points can be sources or sinks, and if they're half source, half sink, it's called a node, or sometimes called a saddle point for reasons that'll be more obvious in 2 dimensions than they are in 1 dimension. But a lot more interesting things can happen in 2 dimensions near equilibrium points. They don't get sucked into or blown away. Well, sometimes they do, but there's other things that can happen. It can get spiral into it or spiral out, can go around it forever. But we can qualitatively analyze this system. Well, we can actually solve it, in fact, and qualitatively analyze the equilibrium point 0, 0, and we'll be able to qualitatively analyze other equilibrium points of more general systems after Chapter 5 using what we've learned in Chapter 3. So that's an attempt to explain why we're going to spend so much time on this simple problem. So we're not going to actually learn how to solve these problems until the next section, but we're going to learn something about the solutions now that will help us in the next section. And the main thing is the linearity principle that says that any problem of this form, now this is not for general systems of equations, it's only for problems that can be written as, y prime equals a matrix times y. They don't have to be 2 by 2, but it has to be written as a matrix times y. Then if you find one solution somehow, and we'll find out in the next section how to get solutions, if you find one section, you can multiply it by any constant and it's still a solution. And if you have 2 solutions, you can add them and you'll still have a solution. And therefore, any linear combination of solutions is still a solution. And remember, that's only for this problem, the problem we're studying in Chapter 3. It's not for the predator-prey problems or more general systems. And it's pretty easy to see why any linear combination of solutions is still a solution. You see, if you take, if y1 is a solution and y2 is another solution, you multiply y1 by a constant, and both sides just get that constant and you can cancel it. So ky1 is still a solution. If you have 2 solutions, y1 and y2, just add them together, and y1 plus y2 still satisfies dy dt equals ay. So any linear combination of solutions is still a solution. Remember that our goal in solving differential equations is not just to find one solution, but find the general solution. Why? Because you need the general solution so that you can apply initial conditions. Real problems will come with initial conditions, and if you find one solution, it may not satisfy the initial conditions you want. They need the general solution with parameters in it, and so you can adjust the parameters to where it satisfies the initial conditions. So we want to find the general solution. So just finding one solution, y1, is not enough. And by the way, a system of 2 equations, the general solution will have 2 arbitrary constants in it, because it's going to have 2 initial conditions. So you need the same number of arbitrary constants as initial conditions. In other words, you'll have first component at 0 is given, and second component of this, if this is 2 by 2 matrix and that's a 2 vector, this is for more general n by n case, but if it's a 2 by 2, like we'll study in most of this chapter, then there's going to be 2 arbitrary constants, and so you can adjust those to satisfy the 2 initial conditions. And in this section, they just pull the solutions out of the hat and say, here's a solution, here's a solution. You can check it. We'll see where they come from in the next section, but you can check it now. If somebody tells you here's a solution, all you have to do is plug this into the equations. You can always take derivatives, and even if you can't solve it, can't figure out where it came from, you can check, x equals 0, y equals e to the t, plug it into here, see that it satisfies both equations, so that's a solution. And then they give you another solution. Now, where they get it from, we won't know until the next section, but you can, plug in x equals e to the 2t, y equals e to the 2t, and you can verify that it's a solution. And so we know now that any linear combination of these 2 is a solution. So the general solution is going to be c1 y1 plus c2 times y2. And now if you want to satisfy initial conditions, you can do that. You can adjust the 2 parameters. That is, you plug in t equals 0 and see what K1 and K2 has to be to make Y come out to be that. Okay, here's an example that's worked out in the text. Here's a 2x2 linear homogeneous constant coefficient system. They give you two solutions that they just use magic to find them. You can check to see that that's a solution and that's a solution just by plugging in x equals e to the 2t, y equals 0. And therefore, any linear combination of those two is a solution. So that's the general solution. Now, if you have initial conditions given, you simply plug in t equals 0 and set this vector equal to the initial conditions, and you'll get two equations for the two unknowns k1 and k2. Solve for k1 and k2, and you have the specific solution that satisfies the initial conditions. Well, that assumes that these two solutions are not just multiples of each other, which they're obviously not, but if they said one solution is just e to the 2t0 and the other one is 10 e to the 2t0, well, that won't do any good because you use 10 e to the 2t0 for the solution there. You won't be able to solve for k1 and k2. You need two independent solutions, that is, solutions that are not just multiples of each other. So, but once you have two independent solutions, y1 and y2, I'm talking about the problem with two unknowns and two equations, and if there were three equations, three unknowns, you'd need three independent solutions, but we're talking about 2x2 systems like this. Then that's the general solution, and then you just plug in t equals 0 and set this whole thing equal to the initial values and solve, like here, solve for k1 and k2. You'll get two equations for the two unknowns, and you'll be able to solve them, assuming these two solutions are independent. You won't if one's just a multiple of the other. Your homework problems in this section, 27, they pull these two solutions out of the hat. Somehow they look like they're just randomly chosen, but they're very carefully chosen, and you're supposed to verify that they are solutions. Well, I think they are. You're supposed to check to see if they are anyway. And once you verify that they're solutions and they're obviously not just multiples of each other, then you can write the general solution as ay1 plus by2, and plug in t equals 0 and set that equal to vector 2, 3, solve for a and b, and you've got the specific solution. So if you could somehow come up with two independent solutions, you'll have the general solution and you can satisfy any initial conditions, but we don't know yet where those solutions come from.